So our first two speakers are from Google. And as many of you know, Google was the first company to adopt OpenFlow and SDN and to adopt that model at scale about 13 years ago. And as time went on, OpenFlow proved too rigid and hard to change. So today, Mythil, Raman, and Konstantin Weitz are going to tell us about Google's experience with P4. And in particular, they've been figuring out how to bring P4's programmability and extensibility into the heart of a switch operating system. Mythil is the right person to be telling us about their work. He's over 20 years of networking experience in Silicon Valley, delivering networking systems, supporting hyperscalers, enterprises, telcos, and Mythil leads the team at Google responsible for the design and development of their internal production networking system. And he drives Google's PINs initiative, which he's going to be talking about, working closely with the ONF PINs team as well. And he's going to be joined today by Konstantin Weitz from his team. Konstantin has a PhD in computer science focused on formal network verification from the University of Washington, and he now leads Google's P4 efforts and is the technical leader of their PINs initiative. So over to you both. Mythil first.
All right, good morning to you all, and I'm glad to join this session of the P4 workshop. Both myself and Konstantin are here to present the PINs work that the team at Google and our partners have been working on. This is a large effort across many people, and we are privileged and honored to present it on their behalf. Simply put, PINs would not have been possible without this coordinated and collaborative team. And I would like to thank all the contributors on. And we've been at the forefront of its evolution for over a decade. Software-defined networking has multiple forms and applications. For Google's network, low-level centralized control of simple networking devices has delivered the necessary performance and flexibility to evolve into planet scale. As Nick mentioned, over the last 10 plus years, we moved from traditional 4-post architecture to a custom cloth fabric, building networks that cater to exponential increase in demand for bisectional bandwidth. This was achieved by simplifying and reducing functionality to what was minimally needed. The internet has grown exponentially by leveraging fully decentralized protocols like OSPF, BGP, TCP, IP, etc. At Google, we've not just relied on best effort or soft state for our application development, but by being able to evolve on the concepts required to provide for higher level network guarantees and SLOs. For certain settings where you're running with a single autonomous system, where the highest level of reliability, availability, and predictability might be required, best effort might not be the rule. We then consider what it makes to take and leverage SDN. The question here is how to leverage a centralized state within a single autonomous system to build a network. We strongly believe that the protocols that leverage a logically centralized state are going to be simpler and more efficient and easier to maintain and get it right over time. Since the entire network state is visible to the central controller, we are able to serialize all intent and state changes through the database. This facilitates faster debugging, as engineers can rely on the fact that the order of changes observed by all applications in the distributed system is same, and therefore we are able to establish the causality very quickly. Our data center fabrics, Jupiters, run on commodity switches across multiple generations of ASICs, and with remote control, driving about 1.3 petabits of traffic per second in the cluster. We leverage an enormous amount of compute on the server rack instead of the switch CPUs to drive these logically centralized decisions. Programmability is a key to our evolution. OpenFlow was the foundation for all our initial SDN development. It was good for switches, but limited for hardware down the road. As our use cases grew, the protocols became more complex. It led to customization and semi-proprietary solutions from vendors. We were unable to leverage traditional vendor gear or the evolving white box scenarios. P4 runtime and P4 helps us solve these problems because it is open, it is extensible, and is customizable. Control plane or from a local control plane running on the same switch. That flexibility is remarkable. Right? P4 runtime is a behavioral interface, meaning that every P4 RT operation has precisely defined meaning through the associated P4 program. This is in contrast to non-behavioral interfaces like BGP or OSPF. This nature can be exploited to aid in validation. For example, one can first analyze a P4 program to automatically generate packets to hit every table entry installed on a switch. And one can then verify the switch forwards these packets correctly by comparing the switch's output packets with the output packets of a P4 simulator. This is very helpful for automated validation and verification. The P4 programs that we write will serve as unambiguous documentation of the underlying data pipeline. This will help to minimize the differences between a vendor HAL and an SDK implementation and serve as a reference for a community at large. Our industry has come a long way in adopting disaggregation and open source. There have been multiple white boxes with merchant silicons being adopted all over. Several open source switches and OSs have emerged that provide distributed and embedded control planes. Each has its own community and use cases. Google also has its own Stratum effort driving a purely SDN switch OS. If you look at it deeply, the communities are solving inherently the same problems around chip and platform management, or trying to add feature capabilities around warm boot, NSF, or protocols. Switch OS by itself is getting to be a commodity, and we see an opportunity in here. Our goals are here to bring in SDN capabilities that we have truly benefited from into a large open source NAS. This would enable the industry ecosystem that has already deployed or invested in a NAS to diversify and leverage the benefits. The larger motivation is to allow the industry, the operators, and the enterprises to incrementally explore SDN capabilities. Operators can run a hybrid control plane. That is, you can run FRR to manage the routing table on the switch and allow SDN to explore a different set of tables, like for telemetry or something else. This incremental approach might get your feet wet and boost the confidence in migration than doing a forklift of the whole control plane. If you look back, you realize that network administrator cannot exploit innovative hardware features because it takes a long time for these features to be exposed through various HALs and to be propagated through the NAS and standard BGP, protocols like BGP. There is an inherent desire for rapid innovation across one language like P4 and can be exposed rapidly. For example, on a programmable chip with a P4-like compiler, network administrators could just extend the P4 program, recompile it, and immediately gain access to a new hardware capability. You could arguably give the control of the pipeline in the operator's hands and allow them to do this work. This could potentially lead to capabilities and features that can be deployed at higher velocity. To quote an example, if you look at the recent paper from Google on Orion, our SDN-defined control plane, the SDN transition from protocols to algorithms, together with the microservices-based controller architecture, enabled us to have bi-weekly software releases. It delivered 30+ feature capabilities, but also helped us improve scale by a factor of 16. Our availability on Jupyter went up by a factor of 50, and B4 by a factor of 100. Remarkable, our network convergence based on the scale, we've been able to improve it by a factor of 40. Such rapid evolution would have been hard, or simply put, impossible, without SDN-based software velocity. With this background and motivations, we are looking to talk about PINs, the P4 integrated network stack, and our efforts in extending open source NAS with SDN and programmability. Looking at the architecture, right, at a high level, a traditional NAS, here's a cartoon picture of what a traditional NAS looks like, with the hardware abstraction layer at the bottom, the database at the middle, and network applications on the top. The smarts of the network all happen in the applications there. You look at protocols like BGP, OSPF, ISIS, as such applications that run on the switch and help build your network topology. You have some sort of CLI, REST, and netconf to push configurations. The packet processing or flow manipulation happens in ASIC. This may be similar to the functions that could be offered in a switch or a SmartNIC or a hypervisor. Though these functions are similar, they do differ in performance. The network application should care about the performance and not worry about how they are processed in the underlying layers. The only way to achieve this is by creating a clear abstraction layer above the forwarding plane that hides the implementation details from what is the physical or the virtual layer underneath. The network applications by themselves should be modular and ideally use all the best practices around microservices and in cloud-native software development, right? They could be developed in such a way that they could run on a switch or a controller or over a cloud infrastructure as well. The extensions or change in architecture that we are proposing here is this lets the SDN controller be capable of doing the smarts that the apps on the switch are doing today. Essentially, you get the flexibility to control the smarts either on the switch or off the switch in your controller and dial up or dial down the knobs based on what you need. It is not one answer or the other when it comes to the question of centralization or decentralization. It's a question of what is the flexibility and what is the knobs that you can dynamically tune when you are in need of a particular use case, scenario, or a deployment case. We believe that this architecture would provide you the flexibility and the capability to transition dynamically in a more methodical fashion. Clear definitions of APIs and data models are required, right? The APIs and boundaries are not just defined between the switch and the controller, but also between various elements within the switch or various components in the microservices there. To provide a NOS-neutral management interface with structured APIs, we propose adding OpenConfig support. This will entail public OpenConfig YANG models to model the switch config, GNMI as a streaming and configuration telemetry interface, and GNOI as a microservices interface for operational commands. Since we are excited about programmability, we are using P4 runtime for programming the HAL. This allows us to send custom programs to the hardware and program them directly via P4 runtime. With this, I will hand over to Konstantin to take us through the implementation and the use case details. On to you, Konstantin.
Thank you, Mythil. Yes, so as Mythil just described the high-level architecture, right? That's kind of NOS independent. I'm going to show you how we're actually doing this for the Sonic network operating system. Do you want to go to the next slide? So what you see here is how we instantiate this architecture for Sonic, right? And as you see, it's almost the same. So basically what we're doing is for Sonic, the hardware abstraction layer is provided by the switch abstraction interface, or SI. We added some programmability features here so that you can make use of P4. And then we go through Sonic's Redis DB and remote the SI through a P4 runtime app that our controller can then talk to. We also have a GNMI app to remote GNMI and GNOI. Maybe go to the next slide. Now, so what we're doing here is that we are modeling the SI pipeline in P4. So this allows you to get access to all the SI features through the P4 runtime interface, right? So this P4 program contains all the usual things that you know and love from SI, right? Like routes, interfaces, next stops, ACLs, all the things, right? There's many more. But what's also really exciting is that, you start with the SI pipeline, but then you can add additional features that you want to leverage. For example, you can insert, here you see just like an extension that you can add to the P4 program after the decap table. And you can then use that extension just like you use any other feature in P4 in SI, right? Through the P4 runtime interface. All right, go to the next slide. Oh, I'm not sure what happened here, but there are some key design decisions that we've made. So first of all, we are very open source friendly, right? We want to open source all our changes. And in addition to that, it's very important to us that we are upstreaming them back to the Sonic community, right? Then another important aspect is all of this is opt-in. So if you're an existing Sonic user, you should see no overhead or impact from the changes that we've made. The next bullet is a little bit scrambled, but what it means is you can mix and match the SDN approach with the existing approaches in Sonic. So you can use, say, BGP to do some computation, but then maybe in a different VRF, you can use the SDN controller. And we're also using familiar interfaces. So, we're remoting PSI, we use P4, P4 runtime, GNMI, GNOI. And lastly, an interesting design decision is that we're remoting PSI, not Sonic. So what that means is you have full access to all the hardware abstraction, all the features at the hardware abstraction layer. And so you have the full power to exploit all of these. All right, next slide. One more. So now I'm going to talk about a couple of use cases that you can use this for. So one thing that we have done very successfully is that we've defined a software-defined wide area network. And the really cool thing here is that we're using, our SDN controller to create very efficient, high utilization of our network. But then we also have a fallback to a more traditional BGP approach to improve our availability. Another thing that you can do with when we update switches, instead of like rerouting or creating a new solution with BGP, we can actually, our SDN controller can reprogram the routes in a hitless fashion, so we don't lose any packets. Another exciting use case is inline network function. So you can continue to run your routing with BGP or whatever you would like, but then you can add functionality like load balancers or firewalls or telemetry through SDN. In-band network telemetry and congestion control in general are other things that can greatly benefit from SDN. And lastly, a use case that I'm going to go into a little more detail here is how we use SDN to do unequal cost multipath, or UCMP, sometimes also referred to WCMP for weighted cost multipath. Right, next slide. All right, what you see here is a completely balanced flow topology. On the bottom, you have the hosts, and then you have a layer of leaf switches, and then a layer of spine switches. Now, if the hosts want to send traffic to the outside of this fabric, we want to load balance all the host traffic perfectly between the spine links. And so how that works is that the host sends traffic. Let's look at the L1 hosts, right? They send traffic to the L1 switch. And then the L1 switch perfectly splits the traffic between the S1 and S2 switches. And then the spine switches also perfectly split that traffic among the uplinks. And so in this balanced flow topology with equal cost multipath, which means this perfectly balanced split, you get optimal routing. Go to the next slide. However, in reality, you almost never have a perfectly balanced flow topology. That's both because you actually have hardware failures, like a link failure depicted here, but also because in reality, you might not want to deploy exactly the number of switches and hosts that you need for a balanced flow topology. And in an imbalanced flow topology, equal cost multipath does not actually work all that well. So here you see a link failure. And in that scenario, even at 75% utilization, which should be handled by this network without drops, you see that we end up dropping packets because we equally send all the traffic to S1 and S2. But we can do better than that. Next slide. So here again, you see what this would look like with an SDN controller. So we add this SDN controller to the side of our network. And the SDN controller, exactly what switches there are, what the links between are, and what the status of these links are. Next slide. So when one of the links goes down, you actually see that reflected in the SDN controller, who gets notified of that through a GNMI event. Next slide. And with that updated topology, the SDN controller can then compute an optimal routing solution and optimal weights for all the load balancing between the switches. So in particular, what that looks like, you see on the next slide. So what you see is that the optimal solution here is for the leaf switches to send 1/3 of the traffic to the S1 spine and send 2/3 to the S2 spine. Next slide. And if you program it like that, you will notice that at 75% utilization, we then end up dropping no packets and fully utilize our available bandwidth. And this is something you really can only do with state-of-the-art technology with using an SDN controller. And something like this is very hard or impossible to do using a distributed BGP algorithm. Next slide. All right, I'm now handing it back to Mythil to give a summary. Thanks.
Thank you very much, Konstantin. In summary, if we at TLDR, we are extending an open source NAS, Sonic in this case, enabling the SDN ecosystem across folks who are used to a traditional NAS and we want to leverage the benefit of SDN ecosystem from the industry. We want the ability to ingest an off-the-shelf switch into our DC, and we want to align the open source community effort on the baseline feature set. And we believe SDN capability, adding that into the baseline feature set is a win-win for the industry. This also enables exciting use cases, as Konstantin talked about, software-defined WAN, hitless route sequencing, INT, inline network functions, and WCMP. PINS as an effort is an incubation at ONF with a few partners. We intend to fully open source this effort by the end of this year. And we already have a few participants who are active in this community, and we're looking for more participation. Please watch out this P4 space for more updates. With that, I think I'll hand it over to Nick for questions and Q&A.
Thank you so much. Thank you both. And anybody that would like to ask questions, feel free to use the Q&A on your. That can work too. I'm going to be monitoring both, but I'll try and I'll probably give more priority to those in the Q&A. I've got a couple of questions that I wanted to sort of start off with, and the first one is that you know, as you pointed out, Mythil, there's been quite a lot of number of switch operating systems that have been developed over the last few years. We've seen many come, we've seen some go. There are some that are still around, and you know, it could be quite confusing for someone who's looking to think about what would make most sense in their environment or where to put their sort of development effort. And I wonder if you any sort of comments about that switch OS fragmentation. In particular, there's a couple of questions in the Q&A about the exposing of Psi and P4 in Sonic versus Stratum. Any comments about that?
Right, and I think that's a good question because, as you said, there's two, I would say, logical camps around a centralized OS and a logically decentralized OS. Right? There have been different flavors of operating systems and different flavors of use cases driving those operating systems. If you look at it deeply, we are looking at different ways of solving the same problem, aligning to our pertinent use cases. Now, the question is, P4 runtime and SCI, how do they, I'm assuming, how does P4 runtime and SCI translate into what we are trying to do? If you look at it, SCI provides the HAL and the abstraction that the industry is converging around. But they do are challenges around how do we get things settled in SCI? How do we get the feature velocity that we require in SCI? And how do we dynamically change things that we want to go exploit, explore, prototype, right? And this combination of remoting with P4 runtime for SCI gives an opportunity for us to embrace the journey without affecting the velocity of community getting together and collaborating on this. Konstantin can add more on the aspects of driving it directly through P4 runtime. Konstantin?
Sure, yeah, I think the advantage of having P4 runtime, right, is really that you can, right, it gives you both the extensibility, right, like by default, you get all of SCI, right, because we model it in P4, but then you can extend it with your own features. Another advantage it gives that I'm, having a programming language background, by your switches, right? And make sure that they actually match your specification in your P4 program.
So this was actually going to be my next question, Konstantin. Given your background in formal verification and languages and compilers, I'm kind of curious how you see this playing out, because we are moving to a time when you can specify the behavior sort of at the top, compile it all the way down to affect the forwarding behavior, giving you multiple layers of abstraction across which you should be able to verify, one would hope. But how do you think this will really happen? Are we close? Are there things that we can experiment with and try out today?
Yeah, I mean, at least inside of Google, we've actually been doing real verification on these switches. We use SAT solvers to analyze P4 programs, generate packets, verify our switches work. There's more than that, right? Like we also do some fuzz testing. I think there's also exciting ideas, right? Like once you have a semantic model of your switch, right, you can see the whole network semantically, right, and reason about your whole network and verify that certain desirable properties are true and so on. Yeah, I think at least within Google, I think we're doing this for real, right? It's not just thinking about it anymore. And I think there are also a lot of the tooling is out there for people to use.
And do you see this as sort of static verification of the code to check that it's not doing something crazy, or dynamic verification during runtime of the way in which the switches are processing packets?
Yeah, we're definitely verifying the actual switches, right? So we're programming flows on the switches, and then we're sending packets, and we're comparing what the hardware does to what the actual software does, right? Or what actual P4 model does. And it's more, right? We verify basically the entire switch stack as well, right?
Okay, and lest there be any confusion, I just wanted to sort of clear up one area that's sometimes confusing, and that is, so you show through P4 runtime a P4 program being compiled and then pushed down to a switch. Should we really be thinking of the controller doing the compilation? How does that actually work? What's the sort of the workflow here that you
Yeah, it's a good point. So we actually compile the P4 programs offline, right? So we compile them as we write. We write the code, we commit it to our source repo, we compile the code, right, and then we push it. But maybe a really important aspect here, I don't know if you highlighted that well enough in the slides, right? This also works with fixed function switches, right? Where P4 program is written in such a way that it really reflects all the fixed function things. So you don't need to reprogram them. Even on fixed function switches, that you usually have some flexibility around ACLs, and that is then derived from the P4 program. But the standard, you don't do anything to the hardware.
Great, thank you both so much. I think we're going to move on to our next speaker now. So thank you, Mythil and Konstantin, very much. Very interesting talk.